Hello everyone. Today in this video we're going to see about A-star search algorithm and with an example of it, and finally we're going to discuss about the application and significance of A-star algorithm. So let's get into it. So as an introduction, A-star algorithm is nothing but a popular pathfinding algorithm that uses graph for traversal algorithm for traversal purposes. Whereas the A-star algorithm is used for finding the shortest path from the start node to our goal node. And it is called as a new strategy that combines both greedy search and then the UCS. UCS is nothing but uniform cost search. Whereas the greedy search will give an efficient algorithm, but it is not a complete and optimal solution. Whereas in UCS, it gives a complete and optimal solution, but it is not an efficient algorithm. So, but A-star algorithm has the both plus points of greedy search and the UCS, whereas it is both efficient, complete, and then it's optimal also. And A-star uses a heuristic function which combines both g of n and h of n. G of n is nothing but the cost, h of n is nothing but the heuristic value. Whereas the formula is f of n is equal to g of n plus h of n. G of n is the exact cost to reach node n from the initial state cost so far up to the node n. So it is nothing but the cost from our initial node to the node where we are in the current node. For example, if there is 10 nodes from 1 to 10, and the one is my start node and 10 is my goal node, and I am in currently in a fifth node, so that the cost will be the g of n will be from 0 to the fifth node, the current node, which is from the goal node, from the initial node to the current node where I am. Whereas in h of n is the estimation of remaining cost to reach the goal. So as I am in the fifth node, from the fifth node to the goal node, which is the 10th node, it is my h of n. From the current node to the goal node, which is considered as the h of n value. So now for an example running through, we will be constructing a graph, which is an example. So we're going to consider this graph for our A-star search algorithm. So here we have 1, 2, 3, 4, 5, 6, 7 nodes, which is whereas the A is our start node and the Z is our goal node. And the black color numbers are the h of n value of these nodes, whereas the green color values are the g of n values of the A to B or A to F or A to C or A to D and etc. And here for goal node, the h of n value is 0 because we have reached our goal state. So there is nothing between there's no value or there's no cost between the current and the goal node. As I am in the 10th node. So if it is the 10th node, then I have to I have to subtract it by 10 minus 10, which is the 0 for the goal node. So for finding a optimal path or shortest path using a A-star search algorithm, we need to construct a search tree for that. For the search tree, we will be using this graph and we will be constructing a search tree. So this search tree contains starts from the parent node and it is explored from B, C, and etc. etc. It goes on. And these black color numberings are the total h of n. Sorry, it's f of n, which is both h of n and the g of n values. So this is what the search tree looks like. So from this search tree, we are going to find the optimal path. We are going to find the optimal solution. So here the Z is our goal node. So there are different types of Z or different ways to find the Z. So you can see here the Z has a 25, here Z has 21, and here the Z has 18, here Z has 17, 45, 46, and etc. There are different ways to reach Z, but we are going to find the optimal path or the shortest path to reach Z. So let's get into it. So now we are going to construct a table which has two main columns, which is open and then closed. And this open column has the four main columns, which is node, g of n, h of n, and f of n. And in closed, we'll be having two main nodes, which is two main columns, which is node and parent. So at the initial stage, we will be taking our parent node, which is A here from the search tree. So we'll be having the parent node as A. We are going to open this node, and as we haven't closed any node as now only we have opened a node, the closed node will be empty list. So now from here we are going to explore the child nodes of the A, which is B and C. So we will be writing C and B here as and one of the most important thing we have to look at this here is we have to write these child nodes while we explore a parent in an ascending order of its f of n. So that will like here we have C and B. Here the B's cost is 16, but C's cost is 14. So we'll be writing it as C and B in an ascending order. So that at the next stage we'll be exploring this C, which tends to find our optimal path, which tends to find our shortest path of our search tree. So that let's have it as C and B here, which is 14 and 16. So now as we have opened the A node and then we have explored the A, we'll be closing the A in our closed column. Just and here we'll be writing the closed node as A. So now as I have already said, we are going to take the least f of n value so that we are going to explore the C here. So here in the C, we are having two child nodes, which is E and D. So now we'll be having B, E, D. From these three nodes, we are going to arrange it in our ascending order. So I'm going to choose it like D, B, E, which is 16, 16, and 17. So I could also choose it as B, D, and E, but it's my choice to choose it as it I want. But at the last, we'll be having our answer anyhow. That there is nothing to consider like why it is there's two 16s and what to do and etc. So I have to get like D, B, and E. So that here we have, as we have explored the C, we'll be closing the C in our closed list. And for this C, there is a parent exists. Here the C's parent is E. So we'll be writing the C's parent as A here. So now here as I'm going to explore the D's childs are E. So that we'll be having this E, and then this B. So here again it is 16, 16, and 17. So I will be arranging like 16, 16, and 17 like here. So this 16 is nothing but from 12 and 4 here. So that this 16 is nothing but from 12 and 4, and this 16, this is B, just having the 16. And as we have having two E's, there are here it is 16 and here is 16 and 16 17. So we are going to explore the least value of the f of m, which is E of 16, which exists here. Okay. So now as we are going to explore this E, so our child nodes of the E is B and Z. So we'll be writing the B and Z, and we'll be closing our E with the 16 value here. And this E has an parent, which is D. We'll be writing it here. So at this point, we're having this B, this Z, and this B and this E, which is 16, 17, 17, and 36. So we are going to arrange this in an ascending order, so that it will come as 16, 17, 17, and 36. So here the B value which has the least f of n is 16, that comes from the parent A. We are not going to we're not going to explore this B. We're going to explore this B as this has the least value, which is from the left side of the search tree. So that we're going to explore this B. So this B's childs are F and E. So we'll be exploring this F and E here, and then we are going to close the B here. So at last we'll be having Z from here, which is 17, and this E from here, which is again 17, and then the E and F which we have explored already. we have explored just now. So that from these values, which is 20, 20, and 17 and 17, again the 17 is the least value, but it has two values. As my goal is Z, I'm going to choose the Z as as the first value, and I'll be sending it as Z, E, E, and F is 17, 17, 20, and 20. So from here, I have closed the B value on from the previous state. I have closed this B value and I have written the parent as A, as the B's parent is A. So at the next stage of this table, we are going to explore this Z here. Whereas while exploring the Z here, we have to close the Z. Then only we could find our path. So that the next step will be just we are going to put the Z over here and we will be closing it and we'll be writing the parent of the Z. So likewise here. So from the previous stage, I have just took the Z and I have closed it. Finally, the goal node is been reached while we are closing our list. So from this state, we will be finding it out. That is the Z that has come from this part is the shortest Z. If we look into it, there are a number of Zs like 25, 21, 46, 18, 45, 17. From these number of Zs, the 17 is the least one, and we have found the least one also. So that this is the most shortest path to reach from the start node to the goal node. Whereas this path will be found out as we have written our closed node Z and its parent as E, we will be going from the backwards. Like from for Z, the parent is E. Then for E, we will be finding here. For E, the parent is D. We will be writing the D here. From D, we will be finding who is the parent. From D, the parent is C. We will be writing the C here. From the C, we will be finding who is the parent. A. Finally, we have reached our main parent here. So that will be finding our shortest goal path with least f of n value, which is nothing but A, C, D, E, Z, which is this path, which has the least h of f of n, and it is the most shortest and an optimal path to go from the start to the goal node. So this H algorithm guarantees optimality and it uses the admissible heuristic. So let's see what it is. So optimal guarantee. A star balances exploration G of n and goal direction H of n. It finds the most cost-effective path among the possible routes. As we have seen in our example, there are different Z, which has 21, 25, 46, 40, 46, 45, 17, 18, and etc. But we have found the value which has the least cost, and that's what it said as. It finds the most cost-effective path among the possible routes. It has different routes, but it will be finding the most cost-effective path and will not stop at suboptimal path if better one exists. Most strong mathematical proof ensures optimality with admissible h of n, which is the heuristic value which we have be having from our graph itself. Admissible heuristics. A heuristic is admissible if it never guesses a cost higher than the actual cost to reach the goal. It gives a safe underestimate of the distance or cost. It ensures A star will not skip the best path, as it has a different number of paths, but still it chooses the best path with the help of the formula f of n, which is g of n plus h of n. Whereas this h of n, the heuristics will plays a major role on finding the best path and not skipping the best path. So that's what it's saying. And because of this property, A star is guaranteed to find the optimal path. It's guaranteed to find the optimal path. Some application significance of Fisher algorithm. So applications we could consider in GPS navigation, shortest and fastest driving route. we'll be using the G maps and etc. Right? So this for this everything we'll be finding the shortest path to reach from our state where we are to the destination where we have to go. So that it's helpful in GPS navigation. Robotics and drones, safe and efficient path planning. So there are some robots like delivery robots or some home cleaning robots and etc. These will be these should be uh, maintained in an efficient way that it uses less electricity or less fuel and etc. For that, if it chooses a best or a shortest path, it will be more efficient. So that and in drones also, if it has to deliver from one place to another place, in an, so that it will be the shortest path will help in reaching the destination in a quicker way and also saving the electricity or saving the battery power or saving the fuel and etc. And it's also been used in video games or NPC pathfinding and dynamic maps. NPC is nothing but non-playable characters, which is in our gaming environment, which helps here as well. And network routing optimizes the packet delivery. So as it is the shortest path, it optimizes the packet delivery and speeds up the network. And logistics, delivery route, and supply chain optimization, etc. Significance. Significance is again we are going to look at what it all we have already viewed. Optimal always finds the best path with admissible heuristics, and efficient reduces time as it is as it is going to find the shortest path. Obviously, it reduces the time and computation compared to the blind search. Blind search, whereas we not be having any information like it is the G of n is not available, H of n is also not available. So it takes more time compared to an informed search strategy. And flexible works with different heuristics for different domains, and widely used in core algorithm in AI, games, navigation, and robotics and etc. So thank you for watching.